All right, so I'll take a look at the assignment today and to make sure that it's reflecting the correct mass matrix in the following steps. Okay, so that there is no other issue in the following steps. Okay, so let us get started. So we talked about the nonlinear stability theory last time, and we basically had this idea that how do we say whether a fixed point in a system is stable or unstable, and what are the stability characteristics, and how can I define a candidate Lyapunov function and verify whether a system is stable or not. We looked at the theory of application of these methods for both autonomous as well as non-autonomous systems. Autonomous meaning that the differential equation didn't have an explicit dependence on time, whereas non-autonomous meant that the derivative actually had an explicit dependence on time. So now we'll come back to our guidance laws, and now we'll start to apply these tools that we learned in order to characterize the stability of the guidance systems which we have looked at so far. So our first, this one is that we'll look at a LOS guidance law for path following using coarse autopilots. So what I mean by here is that we have our marine craft, which is subjected to wind, waves, and currents. And then I have a coarse autopilot, which is basically a controller, which is trying to make sure that my craft's course angle is matching some desired course angle. And I'll assume here that for practical purposes, that the controller is doing its job. We have not yet discussed about control here as yet, but for now we will believe that the controller is doing its job. So whatever desired trajectory or desired heading angle that I'm asking it to track, the craft is able to track successfully. We'll assume that. Okay. Our main focus actually here will be on the guidance law. This is the box that we'll be focusing on, where we'll be taking a look at the waypoints and where is our current position, which means where are we located in the NED frame, and where are our waypoints located from the waypoint database. You will use that to figure out a line of sight guidance law, which will give me the desired course angle. Okay, so that guidance part is what we are looking at. For here, we are assuming that the controller is doing its job. We'll think about tuning the controller at a later point when we start discussing about control. Okay. So the guidance law basically computes the desired course angle, and this is used as an autopilot reference signal for the controller. So one of the first methods which we will try out is called the vector field guidance law. So the idea is that we want the vehicle to get onto the path while moving at a prescribed speed. So rather than having a kinks in the path, we want it to smoothly come and converge onto the path that we want it to follow. And that is where we use this line of sight guidance law, where we are looking at a look ahead distance, so that you're not trying to approach the path that I want to follow perpendicularly, but you're kind of smoothly joining into the path that I want to join. That is the main idea. So we already saw that if we have a craft which is located as shown here, and we have the north axis pointed here, and if the path tangential frame is denoted by XP and YPE represents the cross track error, so this axis is pointing along the it is pointing between the last two waypoints. So it's looking at the distance between one waypoint to the other waypoint. And we are looking at what is the cross track error YPE, and we define the course angle in the projected plane as chi p. So we have seen these definitions before, and we also know that the course angle is actually nothing but the angle pi p plus the angle chi p, because the course angle denotes the distance or the angle between the north axis and the velocity vector, which is nothing but pi p plus chi p. Okay, we have seen this before, so there is nothing new in here. Now, the desired course vector field, we want to define that, and we basically want to say that YPE dot, okay, is equal to u times sine of chi p. And we have seen that as well before. because yp dot, whatever is the velocity along this direction, is nothing but this velocity vector separated into its vertical and horizontal components, and this vertical component, which is u sine of ip, is equal to ype dot. So that's pretty straightforward to understand. So which means that I can write this chi p as chi minus pi p, and we can view now this angle, coarse angle chi, as a virtual control input that we want to steer such that ype goes to 0, such that the cross-track error goes to 0. If the cross-track error goes to 0, we are approaching the path that we want to follow. Everybody with me so far? Okay, that is the main idea. So now what we want to do is we want to take this chi p as minus chi infinity 2 by pi tan inverse of kp times ype. So you can kind of see this as a so-called proportional control, where I'm taking the value of the error, which is the cross-track error ype, multiplying it by some gain value, and then converting it into an angle, and then I'm trying to apply that angle to the chi p vector. You'll kind of soon realize why I am choosing this particular form. Will be clear in just a minute when I try to substitute things back into the place. And it is easy to see that when ype is large, okay, when this fellow is really large, then chi p approaches plus minus chi infinity. Is that making sense? When ype is large, then this tan inverse value will be equal to close to pi by 2. And so therefore what will happen is you're basically, it will either be close to plus or minus pi by 2, depending on whether yp is positive or negative. And then the chi p angle will be close to plus or minus chi infinity. Everybody with me? So which means that when I am far away from my path, I'm always approaching the path at this angle. Okay? But the moment I start coming closer, so when yp is small and tending to 0, you'll see what happens is this tan inverse goes to 0, so chi p actually tends to 0. Okay, which means that even though at the beginning I'm trying to come at a very sharp angle to the path, as I come closer to the path, as my ype is decreasing, I'm trying to merge into it in a much smoother way rather than a abrupt way. Okay, that is what we are trying to say here. And if we assume that our autopilot is perfect, which means that the controller is perfect, then our chi is actually being driven by chi d. Chi d and chi are equal. Everybody with me so far? Which means that our coarse angle is exactly equal to the desired coarse angle. We are assuming a perfect controller at this place. In that case, I can write down my desired coarse angle as pi p minus chi p, and that chi p is nothing but this value. Everybody with me? Yes?
So,
Our chi d is nothing but pi p plus chi p, and chi p is nothing but this fellow right here, and therefore our chi d now becomes pi p minus chi infinity times 2 by pi tan inverse kp times ype. Now, if we look at the so-called ype dot, we know that ype dot is u times sine of chi p, okay, which is nothing but minus u times sine of this angle. Everybody with me so far?
yes, sir. Yeah.
Yeah. Okay. Therefore, Kp basically now determines the rate of transition from x infinity to 0. This value of Kp is our design value, which we tune. It is a it's a gain value which we are tuning to make sure how fast it converges or how slow it converges from an angle of chi infinity to 0 as it moves closer to the path. So we are basically governing how fast does YPE reduce to 0. Its dynamics is kind of governed by the idea that how we tune the value of Kp. Now, we want to also establish that this scheme is always stable. You see, this is not a linear scheme. It is clearly a nonlinear scheme because of the tan inverse which is present there, right? We don't have a straight dynamics coming into picture. We can't solve this differential equation straight away to figure out what the value of YPE's trajectories will look like. Okay, but at the same time, even though I may not be able to solve for the trajectories directly, I would like to at least know whether the scheme is stable or not. This is similar to your the discussion which we had in your maneuvering course, where the system was linear and we were using exponential solutions at that time, and we wanted to understand that whether they will decay down to 0 or not. There we could solve it because it was a linear differential equation. But here we can't solve this because we are looking at a nonlinear differential equation. Rather than solving for it, we still want to be able to say something about the stability of the scheme. And that is where Lyapunov methods really come into the picture. The idea is that for this system, if we can show that the equilibrium point YPE equal to 0 is actually a globally asymptotically stable, then our job is done. We can say for sure that no matter what we do, we will always get convergence. And that is what we are going to look at. So we'll understand what is the stability characteristics of this system. And for that purpose, we will allow for u here, the speed of the vessel, to be time varying in nature. Okay, just so that we can make it autonomous and we can make it a non-autonomous system and still see whether we can guarantee stability at different speeds. Okay. All right. So we know that as long as this chi infinity angle belongs between 0 and pi by 2, we can say that this chi infinity times this value will lie between minus pi by 2 to pi by 2. Okay, that is very clear because tan inverse will always lie between minus pi by 2 to pi by 2. So therefore, as long as chi p is between 0 and pi by 2, our job is done. Okay, this inequality holds. Now we choose our candidate Lyapunov function as half of YPE squared. Okay, and then we are basically saying that this value of V will only be 0 when YPE is equal to 0. For any other value of YPE or any higher value of cross-track error, the value of that function V will be positive. Okay. No matter whether YP is positive or negative, this function will be positive. Okay, so we have satisfied the first constraint of our Lyapunov system, that we have found a function which is only 0 at the equilibrium point and it is positive elsewhere. Okay, our next task is to show that y dot, what is happening to y dot is what we want to figure out. So we'll now take a derivative of y with respect to time, and that will yield me YPE times YPE dot. Okay. Now, based on how we are structuring the guidance law, we saw that YPE dot is nothing but this value right here. That is what we are going to substitute in here. Okay, where YPE dot is actually being governed by a controller whose gains Kp determine how quickly or how slowly the course angle changes from chi infinity to 0. Now, putting that into here, you will actually see that y dot is equal to minus YPE times u times sine of this angle, and that will always be less than 0 for all YPE not equal to 0. So, important thing to understand is YPE times a sine of something involving YPE will always have a positive sign. Okay, if YPE is negative, then sine also will have a negative sign. So the negative times negative will again become positive. Okay, so therefore it can be easily shown that this value v dot is less than 0 for all ype which is non-zero. Because when ype is exactly equal to 0, this v dot is exactly equal to 0. Okay, so except at the equilibrium point, everywhere else this thing is having a negative value, which means that our job is now done. We can apply the Lyapunov's methods for the non-autonomous systems perfectly well. And as long as the speed u is greater than 0, this value will always hold. So therefore, our equilibrium point ype equal to 0 is globally asymptotically stable equilibrium point. Okay, so notice how I did not solve the differential equation corresponding to ype here, but yet I am making some claims about stability. Okay, that is the power of the Lyapunov methods. That is the main idea behind the Lyapunov methods. Okay. In fact, we have shown this to be true for right now for straight line paths, where we are looking at a straight line path between one waypoint to the other waypoint. But you can in fact show that the same holds even when we are looking at curved waypoints. So when you have curved paths along the waypoints, still this phenomenon can be shown. There, instead of taking as the line between the 2 points, you're actually taking the local tangent to the path. Okay. We'll discuss the curved points a little later when we actually start discussing about how to deal with those curved paths. So for now, we will defer that discussion for a later time. Okay, now that was the so-called vector field guidance. Notice that here we were looking at the idea that our course angle, when we are far away from the path, starts at an angle of x infinity to the path and slowly converges onto the path as time progresses, as we come closer to the required path. A special version of this is called the proportional LOS guidance law, where we simply are choosing this x infinity to be pi by 2, which means that I'm approaching perpendicular to the path when I am far away from the path, and I converge onto the path as I come closer to the path. Okay, so a special case of the vector guidance field is when we choose this I infinity to be equal to pi by 2, in which case we can see that our chi infinity times 2 by pi just becomes 1, so we don't have a factor here, and our expression reduces to the chi desired angle, desired course angle is pi p minus tan inverse of kp times ype. Okay. Now, the proportional gain value of kp is usually parameterized in terms of the look-ahead distance. So we typically choose this value of gain as 1 by delta. Okay, and then what happens is basically this becomes chi d is equal to pi p minus tan inverse of ype by delta. And we know from geometry that that always holds in a line of sight guidance law. We have already seen that before. Right? So just to refresh your memory, so if this is my location of the craft, x and yn, our previous waypoint is here, our next waypoint is here, and our along track distance at this point is found by dropping a perpendicular from the craft onto the path joining the two waypoints. Now, at this time, the lateral distance here represents the cross-track error ype, and the distance which we are interested in is so-called look-ahead distance is what is this delta, which is the distance from here till here. Okay, where that look-ahead distance is specified ahead of time. Okay, now you can see that our craft's velocity is oriented along this direction, this one right here, and our craft's actually longitudinal direction, or the body coordinate frame, is oriented along this direction. Then we can say that this angle between the north direction and the line joining the two waypoints is pi p. the angle between the north direction and the longitudinal direction of the craft is psi. The angle between the north direction and the velocity vector is chi. And the angle between the longitudinal direction of the ship and the velocity vector is that crab angle beta c, where if you remember correctly, this is tan inverse of v by u. Everybody with me so far? Very good. Now, we want our desired course angle to be determined as pi p minus tan inverse of ype by delta. Notice that ype by delta basically refers to this angle. This one which is marked here. Okay, we are looking at the right triangle whose base is delta and the height is ype. So ype by delta is that angle. Okay, and I'm basically saying that I want my desired course angle to be pi p minus that value. Okay, so yeah, so this is my desired course angle. Okay. Now we are assuming here that there is a perfect autopilot as before. So again, ype dot is nothing but u times sine of chi p. Okay, where chi p is basically the distance between this and this. This angle here is chi p. Everybody with me so far? It is the angle between the line joining the two waypoints to the velocity vector. Okay. About the path tangential system. So we have ype dot is equal to u times sine chi p, which is nothing but sine of chi minus pi p. And that can be represented in terms of tan inverse of ype by delta. And therefore, this basically becomes ype dot is equal to minus u by square root of delta square plus ype square times ype. So you can just imagine that I have a right triangle whose base is ype and base is delta, height is ype. So the hypotenuse will be delta square plus ype square. So if I want to say I want this sine of this angle, then I have to take ype divided by square root of delta square plus ype square, and that is what I have here. Everybody with me so far? Now, once you have this dynamics for ype, we'll again try to establish the same stability through the Lyapunov methods. And what you'll see here is that the Lyapunov function will be similar to what we chose before, will be half of ype square. So v dot will be ype times ype dot. Okay. So v dot will be ype times ype dot. And ype dot can be substituted from here. Okay, so that simply gives me minus u by this square root times ype square, and that is what I should end up with. And it is again easy to verify here. It's very easy to see here that when ype is positive or negative, this value will always be positive. So therefore, that with the negative u being there, this entire thing will actually be negative for all values of ype which is not equal to 0. Everybody with me so far?
Yes.
Yes. So we have shown again that this point is globally asymptotically stable, which was expected because vector field guidance law had already given that the point would be globally asymptotically stable for any value of pi infinity, which was lying between 0 and pi by 2. Here we have only chosen that value to be pi by 2. That's all. Okay, but the advantage of this proportional LOS guidance scheme is that we can actually show that it is stronger than globally asymptotically stable. We can move for a much higher convergence rate. We can actually set a bound and say that it is semi-globally exponentially stable. And that is what we want to take a look at as to what that extra thing is coming into picture. So we can actually show that this yp equal to 0 is not just globally asymptotically stable, but it is also uniformly semi-globally exponentially stable. That is what this thing means. Uniformly semi-globally exponentially stable. Okay, it is a much stronger condition than global asymptotic stability, but a weaker condition than global exponential stability. So let's try to understand what this semi-globally means and where is it actually coming from. Okay, so I'm going to shift gears and go back to our nonlinear stability theory for a minute here in order to make sure that we understand what's going on. Okay. Okay, all right, there we are. Okay, are you able to see my screen now? What do you see on the screen? Just
Yes, personal.
okay, all right, excellent. Yeah, so we want to look at this idea of uniformly semi-globally exponentially stable of the proportional LOS guidance laws. So notice that there are several guidance laws in LOS which will take this form, and we have kind of just encountered one of such things right now. Okay, the idea here is that we have a system which is defined as dot equal to minus u by square root of delta square plus y square times u, where u and delta we can assume them to be time varying, but they are somewhat bounded in the sense that the delta varies between some minimum value to some maximum value and is always positive, and similarly u varies between some minimum value to some maximum value and is always positive. We're assuming that. Now, we want to show that this equilibrium point y equal to 0 for this system is actually uniformly semi-globally exponentially stable. Notice that this is a weaker than globally exponential stability. In fact, for this system, we can't show that the system will be globally exponentially stable. That is why we'll have to make a settlement. We have to settle ourselves with a semi-globally exponential stability. So GES is not achievable due to the saturation through the trigonometric functions. So notice that this y by square root of this thing came about actually as a sine of tan inverse of y by delta. This is how we got this, right? That is how we came across this form. Because of these trigonometric functions being in place, what will happen is it will saturate our dynamics. Because it's an angle, it will always lie between 0 and pi by 2. No matter how high your YPE goes, it will always get saturated so that your tan inverse of that value will only turn out to be at max pi by 2. Okay. So we don't have a full range of angles which we get, but we are actually restricted in the range of angles we are getting. So this saturation effect is the main reason why actually a globally exponential stability cannot be shown for this particular system. Okay, but nevertheless, we want to say that we can show something stronger than asymptotic stability, which we have already proved because V dot is negative. We want to look at how can we look at a much stronger statement. So you might be wondering, why is this important? We got already asymptotically stable. Are we not just simply happy with it? The question is no, we are not happy with it, because when it comes to robustness of a controller, or robustness in the sense that when there are external environmental disturbances, in respect to that, or uncertain environments are present, how does our craft perform well in that requires us to have a stronger than asymptotic stability in order to beat that robustness. Okay? That is what is basically robustness, how strong you are with respect to dealing with uncertainties. So this USGES provides a stronger robustness properties than UGES, and which is why we are trying to look at what is happening. Again, as we saw before, we had the Lyapunov function V. We defined that as half of V square, and we saw that V dot is basically less than equal to 0, but being equal to 0 when Y is exactly equal to 0. So we already saw that asymptotic stability properties are already satisfied. Now, since V of t comma y is greater than 0 and V dot is less than equal to 0, we can say that Y of t will be less than Y of t0. So beginning wherever I started from, as time evolves further, I can say my trajectory actually will be shrinking in some sense because of the asymptotic stability. Is that making sense?
Yes, okay.
Yes? Okay. So now we have Y of t is less than equal to Y of t0 for all t greater than t0. And we already know that this origin y equal to 0 is uniformly stable, and in fact it is GAS, we have already proved. So let's now define a function phi, which is given by u divided by square root of delta square plus y square. Okay. Now, if we choose a value of a radius greater than 0, and we find that y of t is always less than r, okay, for each r greater than 0 and y of t less than r, we can say that as long as the trajectory is less than this circle of radius r, phi of t comma y will be greater than this some value of c of r, where c is a function of r. Okay, please understand this again. I'll repeat this one more time. The idea is, as long as my trajectory is staying inside a circle of radius r, I can show that this function phi, which is defined by u divided by square root of delta square plus y square, will always be greater than equal to u min by delta max square plus r square. I'm just finding a bound for that function. It is very clear here, right? The minimum value of this phi will be where u is minimum and delta is maximum and y is maximum. Right? Where the numerator is minimum and the denominator is maximum, that is will be the bound of this function. And that is what I am substituting. The minimum value of u is u minimum. The maximum value of delta is delta maximum. Maximum value of y is, it is inside a circle of radius r, so I am simply substituting r square. Okay, so therefore I can always say that this function phi will always be greater than equal to c, and this c is a function that I am defining as equal to this value. So when I look at my v dot, which was now given by minus 2 times phi times v, so let's see what happened there. So when we were looking at v dot, we were looking at this value, okay, is nothing but phi, okay, and y square is nothing but, I can write it as 2 times half y square, where that is v. So this whole thing can be written as minus 2 times v times v. Is that making sense? Alright, so I'm saying that this thing is equal to minus 2 times phi times v, and because I know that phi is bounded by C of r, I can put an inequality is less than equal to minus 2 times C of r times v for all y which is lying inside this radius r. Everybody with me so far? Okay, alright. Now, let's imagine that I have a linear system. Suppose I had a differential equation z dot is equal to minus 2 times C of r times z. I know that its solution can simply be given as z of t is equal to e to the power minus 2 times C of r times t minus t0 times z of t0. This is a straight linear differential equation which we have seen before. Okay. There's nothing very complex about it. We can simply find its solution. Now, in a similar manner, I can say that v of t, okay, with a trajectory y of t is less than equal to e to the power minus 2 times cr times t minus t0 times v of t0. Because you see, what I am saying is that v dot is bounded by this. So whatever is the solution for that v coming from this equality where v dot is equal to minus 2 times C of r times v, those solutions will always lie less than equal to the solution where the equality holds for v dot. Is that making sense? I'm saying that I'll find out the location where, see, this is an inequality less than equal to, right? Wherever this equality holds, I'll find the solutions for that, and that will be given by my right hand side here, e to the power minus 2 times C of r t minus t naught times v of t minus y of t naught. Similar to what we had as the z system, right? In reality, v dot will be less than this for the original system. So the trajectories will either fasterly decay or at max decay at this rate. So therefore, y of t will be either less than or equal to this value which you see here. Is that making sense? Tell me yes, no, can't see your faces. Yes, everybody confident with it?
Can you please repeat it?
Yes. See, Krishnavelu, the idea is v dot is less than equal to some value here, right? I am taking the equality and then solving that differential equation to get what v of t comma y will look like. Okay. Whatever value of that I got is actually written here on the right hand side. That is the solution of the differential equation. Okay, because v dot is less than equal to this value, which means that the v will decay faster or at max at this rate. So therefore, my actual solution will be either this or will be smaller than this. If it decays faster, it will be smaller than this. Okay, so y of t comma y will be less than equal to this e to the power minus 2 times cr times t minus t0 times v of t0 y of t0, where this is the initial condition. This is the starting time. This is the value at starting time. I'm saying that any further point in time, v of t will be smaller than this bound. Okay. Now, we know that this v of t is nothing but half of y square, right? We know that that is nothing but half of y square, which means that if I substitute that, I can say that mod of y of t will be less than equal to e to the power minus cr times t minus t0 times y of t0. Okay, basically that's 2 vanishes from that exponential when I take the square. That's all is happening. So what is this telling me? That it is telling me that as long as I choose a value of t0 to be less than r, I can always find that this y of t will have an exponential decay which depends on the chosen value of r. The bound will be some chosen value of r, c of r will determine how fast my solutions decay. That is why this is semi-globally exponential. If this C of R was independent of R, I would say it is exponentially stable. Okay, only when, because if I choose the trajectories to be inside some radius and I want them to decay down to 0, their decay rate will depend on this value of R that I chose. If that dependence was not there, then it would be globally exponentially stable. Without that, it is semi-globally exponentially stable because it actually depends on the value of R that I choose. Okay, are you able to understand what I mean by that? Yes, no?
Yes, sir. Yeah.
Aditya, yes? I see a confused look on your face.
Yes, sir. Like, could you explain about the C function C of R?
C of R is nothing but this thing, no? This minimum value of thing which we chose. It's a function of R simply. For a given value of R, it is simply you plug in R here and find the value of C, that's all. It is basically only telling you, Aditya, that if I chose the trajectories to be inside some radius R, I can say that they will decay at a rate which depends on that R.
Okay.
It just tells me that this y of t will have an exponential convergence, but the rate of exponential convergence is not uniform across all this one, but actually depends on how big an R you chose.
Yeah.
So it basically means that, let's say if I were to draw a circle and say this is the R I chose, then you may say that yes, its convergence might be e to the power minus 2t, maybe faster than that. But if I chose a bigger value of this one, for that the corresponding convergence might be exponential minus 3t. The fact is that depending on the radius of that y of t being inside a radius of r that I am choosing, the convergence rate will depend on that r that I chose.
Okay.
Okay, that is why it is semi-globally exponential. It will always be having some exponential decay, but the rate of convergence is not uniform across the entire domain.
Yeah. Okay.
Okay, so that
Yes.
is why this is semi-globally exponential. If this C of R was independent of R, then I would simply call this as uniformly globally exponentially stable.
Yes.
So the idea here is that by doing this exercise, we are showing that this thing is semi-globally exponentially stable, which means that we are making a stronger statement than asymptotic stability, but it is weaker than globally exponentially stable. But nevertheless, this semi-global exponentially stable is good enough for most cases to say that yes, we can deal with disturbances. Our control logic or our guidance law is robust enough to deal with any disturbances which are coming into the picture. Even when there are disturbances, it will still experience a exponential decay, which means I will see a convergence happen, only that the rate of convergence might depend on where I am, how far away I am. Okay, is that making sense? Yes.
Yes, sir.
Yes. Everybody, yes. I'm seeing a few confused faces. If not, tell me. We'll talk about it more. How many people want it to be discussed again? everybody is okay with it?
Sir, the main difference between this semi-globally and normal exponentially stable, it is the exponent. Like the exponent is
Correct.
constant.
Exponent is constant. It doesn't change with depending on how far I am taking. So let's simply say I have y dot is equal to minus 2y. Okay. We know that this fellow's solutions are e to the power minus 2 times t minus t0 times y of t0.
Yes.
We know that its solution is that, right?
Yes.
Here its exponent is fixed. No matter how far away I choose a y, it will always decay with an exponential decay at a rate of 2.
Yeah, constant rate. Okay.
Whereas what I am saying is in the semi-globally state, it is not so. Depending on where this y of t0 lies, in what radius it lies, this C of r will determine the exponential convergence rate.
I didn't understand one point. Like this, why is this a weaker this semi globally? Why is it a weaker of stability?
It is a weaker form of stability because let us say that the convergence rate as r increases, this C of r may become much smaller.
Okay, it is in the denominator. Okay.
Right? It will become much smaller, which means it is not converging quickly enough. Whereas a uniformly globally exponentially stable system will converge much faster.
But it will still depend on the constant, right?
Right. It will depend on the constant, but the point here is being the further away you are, there will be a limiting point. Always there will be a limiting point
Ah,
where
okay.
your convergence will become lower than any chosen value of exponent.
Okay. Okay. In C of R, it is inversely proportional to R, like more or less.
Yes. So as R increases, C basically decreases.
In that sense, yes, it will be. Yes.
Starting from
So it is a
further away,
weaker convergence.
Yeah.
Go ahead, Vallar.
like just that starting further away out, it is slower, but getting closer to the equilibrium, it is faster.
It is faster, and that's precisely why it is the stability we are unable to prove to be globally exponentially stable, because when it is very far away, that saturation element is coming into the picture. Your tan inverse is simply becoming pi by 2. It doesn't change from pi by 2 by much. That is why this saturation effect is coming into the picture.
Yeah.
Okay. All right. Okay. Hopefully we have kind of looked at it now. Take a look at it one more time, and if we have still more questions, we will definitely try to revisit the topic. But the idea here is that we are able to say that it's a stronger concept than simply asymptotic stability, but a weaker condition than a globally exponentially stable. But since we have this semi-globally exponential stability, we can actually talk about robustness. And we'll talk about robustness much later when we start dealing with control, because that is where really uncertainties into controllers will be dealt with. At that time, it will become more clear as to what we mean by this robustness properties. But please understand that an exponential convergence is very much required in order to show that the system can be robust enough. Without an exponential convergence, it is very difficult to demonstrate robustness of a system to various kinds of uncertainties in the model. We'll talk more about that when we talk about controllers. At that time, we'll discuss robustness as well. Okay. For now, just understand that this property will be useful at that time. I have not discussed that property right now, but at that time, we'll discuss it and try to put it to rest. Okay, so the main idea here being what we have looked at today is this line of sight vector guidance law, and where we were approaching the path at some angle x infinity when we were very far away, but smoothly converges onto the path as when we get closer to the path. So when our cross-track error becomes closer to 0, we try to approach the path tangentially. And the idea was that that value of gain kp that we were looking at determines how fast or how slow we make the transition from x infinity to 0. Proportional line of sight control guidance law basically is, line of sight guidance law. There's no control there, okay? Proportional line of sight guidance law basically tells us that when we are far away from the path, we are trying to approach perpendicular to the path. Okay. And then as we come closer to the path, we are kind of trying to curve into and join the path that we want to follow. And here we are able to show a much stronger dependence, where we are able to prove that the equilibrium point, which is ype equal to 0, is not just asymptotically stable, but is rather semi-globally uniformly semi-globally exponentially stable, which is a stronger condition than asymptotic stability, and that helps with keeping our system robust to uncertainties which we may not have modeled in our system. Okay, that is the main summary of what we have looked at today. Okay, let me stop here today, and next class we will try to understand a slightly different style of a what you call enclosure based LOS steering, and we'll see what are the difference between a look ahead based LOS and an enclosure based LOS. Always a look ahead based LOS is better preferred compared to enclosure based, but for a sake of completeness, we'll just look at what that entails and why is that computationally more expensive. Okay. All right, that will be all for today. Let me stop recording now. Unless there are any questions. Are there any questions? Okay, so let me stop recording.